All right, so we're going to do a lab and investigate some collisions. So first of all, if you look at the cart on the table in front of you and you give one or both of them a little nudge, a little impulse, what does it do? Okay, so what does it have then because it's moving? It's a velocity, which means that it has momentum. And it has a velocity, so what else does it have or possess? Because kinetic energy, good job. So momentum is calculated by the product of the mass and the velocity. Do you remember what kinetic energy is? Very good. Okay. And yesterday we went through and we used Newton's third law, that for every force there is an equal and opposite force between two bodies, to show like the result of doing that and substitution was that the sum of the final momentum is equal to the sum of the initial momentum. And that led us to say that this shows that momentum is conserved. Now, we also have studied energy already. And what did we learn about energy in the world and the universe and the systems? It's never what? Created or destroyed. Therefore, it is conserved. Very good. So, energy, the final energy a system has, must equal the initial energy. Now, some energy can be transferred from the system to other objects or things, bodies. But this is the conservation of energy. So what I want to know is the answer to these questions. Is momentum conserved during a collision? Now the math says it's so. But maybe we should test it. And what I don't know is, is energy also conserved during the collision? So if you want to determine the momentum of your cart or the kinetic energy of the cart, what vital piece of data do you need? The velocity. The mass is something that we can use the scale to measure, but we need to find the velocity. So we need a way to capture or determine the velocity of our carts before and after they interact with each other. So the setup you have in front of you is a track, and on that track there are two carts, and there is a photo gate. So it kind of looks like a little thing like this. And there's another photo gate over here. And you've got the carts. So the photo gate has a little tiny eye on it where a infrared beam, which you can't see, but I'm drawing as red here, is produced. And on top of the cart, there's a picket fence. and the picket fence is striped. And all of those stripes are equal width. So just like the garage door opener, maybe, or not garage door opener, but there's a sensor usually on a garage door, usually at the bottom where the garage door closes, that if something is in the way, the garage door will not work. So it's the light cannot pass through, therefore the circuit is not complete, and so it doesn't work. That's basically what happens. So as the picket fence passes through the photo gate is cut, or the infrared beam is cut every time a solid bar goes through it. Each of those solid bars are equal width. They're all about 1/2 centimeter in width. So if you have the time and the distance, what can you find? If you just have time and distance, speed. And if you have the time and distance for several of events, so there's like 13 little pickets on your picket fence, then you will have 13 data points, 13 little speeds versus distances. Not the right word. Distances and times. And so the calculator takes that information and will give us a distance time graph and a speed time graph for each one of our carts. The problem is the photo gate does not know which way is positive and which way is negative. It will only give us distance and speed. So we have to put the signs on there. Okay? So if you look at your photo gate, one of them has a blue dot on it and one of them has like a red dot on it. That was not red. Okay? That's to help you determine which cart is which and keeping up with the direction and things like that. Because we can set our calculator to make the colors of the graphs match the colors that we've assigned on the gates. So if this cart right here is my blue cart, and you give it a little nudge this way, well, in most coordinate systems, this is the positive x direction over here, and this is the negative x direction. So that way is negative, this way is positive. So what would the velocity be, positive or negative, as the blue car goes through this gate? Positive. But the red car over here that also has its own little photo gate and its own little picket fence that should be equivalent, but it's red and it's moving this way. So what's its initial velocity, positive or negative? Negative. So you will only be able to find the speed. You have to make sure you keep up with what sign needs to be attached to that speed. Okay? Then if we have two different collisions, if you look at your cart, there's one side of the cart has Velcro on it. It has a pile and hook. The hook is like the scratchy part. The pile is the fuzzy part. And it allows the two carts to stick together. If you put the opposite sides towards each other and you push them towards each other, so go ahead and do that. So not the fuzzy Velcro sides. So put the non-Velcro sides towards each other and just give them a little push towards each other. What do you see? They bounce off? Do they touch each other? We don't want them to touch each other. We want it to be like an invisible spring between the two parts, okay? So after you did that, which way was the blue cart moving after the interaction? Right, so when you look at the data, you've got to put a negative sign on the final velocity of the blue one because it bounced off. And the red one also flips signs because it bounces off. So you have to keep up with the direction. That's really important because momentum has a sign. Okay? Now, Then we can do the Velcro Experiment, so the Velcro Collision, and for that one, start out with one of your carts here in the middle and at rest between the two photo gates. Oh, that's ugly, but anyway. So this one will start out here. Make sure there's enough room though for the blue cart to get all the way through the first photo gate before it hits this one. So there'll be Velcro here and Velcro here. If you try that, so put one of them in the middle. Put the Velcro to Velcro. Okay. Make sure the one in the middle is positioned so that the first one gets all the way through the gate before it hits the second one. So this is our blue one, and this will be my red one. And I need my red one to be far enough away that they both get through. All right, so if you give the blue one a nudge, give it a little impulse. Boop. So you may have to give it a little more to get it to go. But do you see that they stick together?
Does the red one have to come?
It does not have to. Good question. Okay. So those are the two collisions that we're going to look at, two interactions. Now there's also a block on your table that has a screw and a cap on it. That is a mast. So once you've done all the collisions with equal mass carts, you can put the extra block on one of the carts and try the collisions again. So then you'll vary mass and see what you get. Now, you know me, so we got a claim or we have a question. Or I guess the claim really should be that, we believe that momentum and energy should be conserved because that's what the math says. That's what the rules say. So we need to collect some evidence. So our evidence would be our velocities so that we could find the momentum before and after. And we can find the kinetic energy before and after. And we always create a graph to show a relationship. So I'm going to give you a hint. Okay, so if I'm gonna plant a seed for you. Okay, so here we go. If I tell you that A is equivalent to A initial, okay, and I wanted you to graph that. All right. So what would that look like if I had, remember the general equation for a line is y is equal to mx plus b. So what would you graph if you had A is equal to A initial? Because the correlation would be, yes, the slope would be 1. That would be A on the vertical axis and A naught on the horizontal axis. And if it's perfectly correlated, the slope should be 1. So if you want to prove that one thing is equal to another, if you want to prove that one thing is equal to another, then you should be able to graph them and see a correlation. Okay, so